We spent several days now talking about non-uniform fields, although we didn't necessarily specify that they were non-uniform fields. Electric fields that looked like this. A radial field that surrounds a positive charge or a negative charge. The strength of that field varies depending upon location. The strength of the field here is greater than the strength of the field here because the field lines are closer together. They're a higher density at that point. That's why we call it a non-uniform field, because the strength varies depending upon where the point is. We can calculate the field caused by that positive or negative producer by using the producer equation, E is equal to KQ over R squared. Now, we also have another equation that we can use if we have something experiencing the field there. If there happens to be a positive or a negative charge experiencing the field, we can also use the equation E is equal to F over Q. Careful with the charges here, though. This charge is the charge of the blue one, what caused the field. This one would be the charge of the green one here, what experienced the field. Yesterday we learned about uniform fields. If we have a uniform field, it might look something like this. Two plates, positive plate on the top maybe, but negative plate on the bottom maybe, with an electric field going away from the positive and toward the negative. It's a uniform field. We know that because the field lines are parallel to each other. It doesn't matter where you are, right here, or right here, or right here, or right here, the field strength is exactly the same. We can't use the first producer equation anymore. We have to use a new producer equation. And that new producer equation looks like this. E is equal to delta V, big V, not little v, because little v would be speed, big V, electric potential difference divided by distance, the distance between the plates. And remember, D, not where the charge is, not how far the charge has moved. We don't even know if there is a charge there, but rather just the distance between the top plate and the bottom plate. What does delta V stand for there? That was that new term yesterday that wasn't familiar with us. What does delta V stand for? Yeah, it's the potential difference, right? It's the difference in energy, between the two charges. Sorry, between the two plates. The difference in energy per charge between the two plates. Does that make sense? Yesterday we used the analogy of money per person. Well, here we're talking about joules per coulomb, the amount of energy per coulomb of charge, and it's the difference in that between the two plates. Typically, that number would be given to you. Now, if you happen to have something experiencing the field anywhere, it doesn't matter where, because it's the same value anywhere between those plates, we can also use the experiencer equation that we had already learned, E is equal to F over Q, using the charge of the experiencer if there happens to be one there. So, we summarize that with a nice little Venn diagram. We got our first equation, our first producer equation, KQ over R squared. We have our second producer equation, E is equal to delta V over delta D. And in the middle, we have our experiencer equation, E is equal to F over Q. These two, I should circle those in another color actually. These two, it erased more than that. There we are, finally. These two go together because they're valid for that first situation of my non-uniform field, the field that looks like this. These two we group together because they're valid for my uniform field. That's the situation where we have two charged parallel plates. This time I'll put the top plate as negative and the bottom plate as positive. The field goes upward this time, again, away from the positive toward the negative. Now, we talked about this yesterday, right? We don't see in an everyday world two charged metal plates all that often. It does happen, but it doesn't happen all that often, right? The exception might be the bumper cars, you know, at Calais Park or at West Edmonton Mall, where you have a metal plate on the top, a metal plate on the bottom, they're both charged, and you get a uniform electric field between them. But we don't see that on an everyday scale very often. You do see it in more not microscopic per se, but smaller scales that we don't often see inside electronic devices. Okay, you can have two charged plates that are parallel to each other, a capacitor it's called. But more often than that, okay, we see things like this, approximations of parallel metal plates. Maybe we've got a cloud that's negatively charged. Maybe we've got the Earth there that's developed a separation of charge such that the top of the Earth is positive. Those aren't metal, and they're not quite parallel to each other, but they're close. Close enough that we would say we would have a pretty uniform electric field between the cloud and the ground there. So we could analyze that situation using the same mathematical analysis as we analyze the two metal plates, right? We have kind of the theoretical, and then we have the practical that isn't quite perfect, but it's pretty darn close and can be analyzed the same way. Make sense? Okay, we have 3 questions for homework. Let's give you some answers to those questions, and then we'll decide which questions we need to go over based on what those answers are. All right, so you don't need to go over any of those questions. Okay, one question though, how do we justify essentially that newtons per coulomb is a volt per meter? Okay, let's use a unit analysis to let's learn to speak, and then let's use a unit analysis to show that those two are equal to each other. All right. So let's start with a newton per coulomb here. We could say that newton comes from the equation F is equal to m times A, agree? And m times A would be kilograms. You know what, actually, let's go the other way around. Okay, let's start with a volt per meter, actually. Should be able to do this either way, but let's start with a volt per meter. A volt is a unit of potential difference. And potential difference is the difference in energy per coulomb of charge. So a volt would be the same thing as a joule per coulomb. Agreed? So let's sub in a joule per coulomb for this. That becomes joules per coulomb over meters. Or we could say joules per coulombs times meters. Agree? All right, we're still not there, right? But we're getting there. Let's now replace a joule with something. There's several equations that we have for energy, right? EP is equal to mgh for gravitational potential energy. EP is equal to, or EK, sorry, is equal to 1/2 kx squared. EP is equal to 1/2 kx squared for spring potential energy. EK is equal to 1/2 mv squared. Yeah, we can pick any of those. Let's pick 1/2 mv squared. And let's replace a joule. 1/2 mv squared would give us a kilogram times a meter squared per second squared. Right? 1/2 m times v squared. V is meters per second. V squared would be meters squared per second squared. Okay, make sense? So now let's sub that in. Now we got kilograms times meters squared per second squared over coulombs times meters. Good? Okay, so now let's see here. Let's cross off one of the meters, because you got one on the top and one on the bottom. That simplifies things a little bit, right? And if we're going kilograms times meters over second squared times divided by coulombs, that's the same thing as saying kilograms times meters over coulomb times second squared. Good? A newton comes from force, which is m times A, which is kilograms times meters per second squared, right? Mass times acceleration. So we can replace a kilogram meters per second squared with a newton, which ends up giving us a newton per coulomb.